Hello, this is Dr. Christy Patton-Lokes, a chemical engineering professor at Missouri S&T. This video lecture is going to be on the concept of equilibrium, designed for the intermediate thermodynamics course. Our goal for this lecture is that you will be able to define the criteria for equilibrium in a pure substance. So let's look at some basic calorimeter problems. And we'll first look at the system designed to evaluate thermal equilibrium. So we're going to have a calorimeter. We're going to have different material on the two sides of this calorimeter. These materials are separated by a partition that is impermeable, meaning no material can travel through the partition, and immovable, meaning it's in a fixed location, so the volumes will not change. And we're going to allow heat to transfer across this partition. So this means that the number of moles on side A and side B will remain constant. The volumes on side A and side B will remain constant. But the internal energies on the two sides can change due to that heat transfer. Since S is the sum of the entropy on side A and side B, we know that from the second law, entropy is going to increase throughout the process, which means it will eventually reach a maximum once no more changes happen. So that differential ds is the change in S on side A and side B. And what's going to happen is that when we use the fundamental relationship for S, so taking the one for du and rearranging it for ds, then we end up with an expression where if dv and dn are 0, we're left with just 1 over t on side A du on side A plus 1 over t on side B du on side B has to be the sum of the total change in entropy. But because there's conservation of energy inside this system, the internal energy change from A has to be the same quantity but opposite sign of the internal energy change of B. And so in order for us to get ds equal to 0, this implies that TA has to equal TB in order for ds to be 0. So at maximum entropy, we're going to have thermal equilibrium, meaning that the temperature on side A will equal the temperature on side B. Now, if we look at this and say that on side A, if the entropy increases a little bit, then this is also going to increase the U. Again, look at the fundamental relation. And so the temperature of side A initially will be lower than what it is finally. The temperature will increase. On side B, if that entropy were to increase a little bit for side A, then on side B, that entropy would need to decrease by the same amount, meaning that UB would be lower, and so the initial temperature on side A would be more than the final temperature on side B, which is an indication that the heat is traveling from a high temperature to a low temperature. But more normally we look at this as a definition of thermal equilibrium, that the temperature on side A is the same as the temperature on side B when entropy is at maximum. So let's now look at mechanical equilibrium. So a similar situation, but I'm going to change my partition. So I'm still going to have the material on two sides with fixed number of moles, volume, and internal energy. The partition will be impermeable, meaning that no moles can travel, but I'm going to allow it to move like a piston. So the volumes on the two sides can change. I'll also still allow heat to transfer through the partition. So in this case, NA and NB will be constant throughout the problem, but UA, UB will change, VA and VB will change. Again, if we're going to equilibrium, entropy is going to reach a maximum, and so when we look at my ds as the sum of the change in entropy on the two sides, for this expression, if dn is 0, I still have the du and the dv terms. For side A and side B, there is written here. So if we look at this, internal energy gained by A has to be lost by B. Volume gained by side A would be lost by side B. And the only way for all of this to be true is that the temperature on side A will equal the temperature on side B at equilibrium, and the pressures on side A and side B will be equal to each other at equilibrium. Now if you fix a constant temperature path to approach this maximum entropy, then we see that the T's can be factored out, and so PA minus PB dV divided by that common temperature is going to be my change in entropy. We know that ds is increasing, okay, always during the process, and we know that temperature has to be positive, and so that means that if the volume on side 1 increases, P1 has to increase, and if volume 1 decreases, then the P1 is going to be less than P2. So volume is going to transfer up the pressure gradient. Okay? As you apply more pressure, you're going to have smaller volume, and vice versa. This is mechanical equilibrium. Again, we've added the requirement that pressures are going to be equal on the two sides. Our third category is mass flow equilibrium. In this case, I'll let the partition be rigid, okay, meaning I'm going to fix the volumes on the two sides. Semi-permeable, so that material can travel across from one side to the other through pores in this partition. But I'm only going to do that for component 1. Molecules for component 2, they're too big to go through these pores. And I can either let it be conducting or not. It's not really going to make any difference because energy will in fact travel across the partition due to these pores. If material flows, it will carry internal energy with it. So I can look at a material balance on component 1, and the number of moles on side A is going to change in the opposite direction but same quantity as the number of moles in side B. And the internal energy similarly will change the same amount but opposite quantity for sides A and B. So if you look at what happens to ds, we see that not only do I require that the temperatures on the two sides be equal, but also that at equilibrium the chemical potentials for component 1 will be the same on side A and side B. Now you can look at a lot of other cases. You can start with any fundamental relation and fix various variables. Ones that are particularly interesting for us would be the case of fixing the number of moles on each side, the temperature on each side, and the volume on each side. And then look at how changes in A are affected. And what you learn is that if S reaches a maximum, then A must reach a minimum. And if you look at a problem where you're fixing the number of moles, temperature, and pressure on each side of the calorimeter, and look at changes in Gibbs energy, then you find that when S reaches a maximum, the Gibbs energy must also reach a minimum. A table in our textbook summarizes this for various systems. And I'm just going to leave this here. You can pause and look at this. We will, in the next video lesson, be looking at stability criterion, the final column of this table. Thank you for your time.